So now we are going to discuss next part of Irodov physics problems, and the name of that part is elasticity, and basically we will talk about stress and strain, etc. So next question is 1.296. A thin uniform copper rod of length L and mass m. There is a rod of length L and mass of this rod is m, rotates uniformly with angular velocity omega. It is rotating uniformly with angular velocity omega in the horizontal plane about a vertical axis through one of its end. Okay. Determine the tension in rod as the function of distance. We have to find out tension in rod. So we have to find out two parameters. One is elongation and second is tension. So as we know that if this rod is rotating, then tension at this free end will be equals to 0. Okay. So let's take a small segment at a distance r. Suppose length of this segment is dr. Okay. So if tension is T at this point, then at this point this tension will be T plus dt, which is reducing as we are moving away from this end. Okay. So this tension difference between these 2 points will be equals to force due to this circular motion or due to this rotation on this particular segment. Okay. So the difference of tension T minus T plus dt is equals to force acting on this segment, that is dm r omega square. Okay. Now we can get dm for this segment, that is mass per unit length into length of this segment. Okay. So from there we'll get minus dt is equals to m over L omega square r into dr. Okay. So now we can integrate this function. When length r is 0, tension is maximum. Okay, or at any point r we can take. Let's take any point r. At distance r, tension is T, and when distance is L, tension is 0. Okay. So from this integration we'll get T, and that is equals to m over L omega square, and this integration is r square by 2, so we can take half here, and this is L square minus r square. Okay. So this is function of tension which is changing with respect to this distance r. R is the distance from this rotational axis. Okay. Now our next point is to find out elongation in this. Okay. So for elongation we can apply a concept that strain is equals to stress upon coefficient of elasticity. Okay. So the coefficient of elasticity we already know. If we assume the cross section of this rod is S, okay, so we can write that the strain is change in length upon original length. We are working for this small segment, that is equals to stress. Stress is force divided by area. Force is this tension T upon area into elasticity. Okay, modulus of elasticity I must say. So this is T del E is equals to, we can use this value 1 over m omega square L into E into S into L square minus R square into dr. Okay, now we have to integrate this function, so we can integrate this for entire length. So this is 0 to L, and this is also 0 to epsilon. Okay, so we'll get epsilon is equals to 1 over 2 m omega square L Okay, here I am writing again small n and capital L. So please don't get confused, both are same. Okay, so this is L E into S and this is L square minus R square. Okay, so if we'll integrate this part, this is L square into R. Okay, and for second part, this is same constant 1 over 2 m omega square L into E into S into R cube by 3. Now we can substitute limit 0 to L. Okay, so if we'll put limit here, then what we'll get? Epsilon is equals to 1 by 2 m omega square L into E into S. This is L cube by 2 if you put limit here, and this is L cube upon 6. 2 into 3 is 6. Okay. So after simplification, what we'll get? That this is 6, so 3 minus L cube upon 6, so this is L cube upon 6. So we'll get L cube upon 12 into m omega square L into S. Okay, into E. Okay, so we can just rectify this, remove one more term, and we may write that the sigma is equals to L square upon 12 into mass. Mass we can write, mass is density. Density is given in the question. It is not given although, but we can use density into volume. Volume is surface area into length, just to minimize the term. Okay, and omega square upon S into E. So some terms will be eliminated from there. So this is zeta is equals to L cube omega square rho upon E into 12. So we can write our answer in this term. So this is our final